So far, I have presented the DSA or DSAnalysis toolbox by means of a very simple RLC circuit. I have presented the different files that you need. I have presented also examples of the collocation methods and examples of the time domain simulations. Now I will continue to cover the features of this toolbox, but by relying on a slightly more elaborate system. We'll go to an MMC system with the circulating current controller and only one phase. So in this circulating current controller, actually, it's not just a circulating current controller, there is also an alternating current controller. You have access to all the details of this system in chapter 1 of my PhD thesis. This is the simplified single-phase MMC model. I have already implemented the equations. I could go to the systems and then to the MMC and then to the circulating current controller implementation with one phase here, and I could open them all like this. However, I would like to present a shortcut to do so. Since I have defined the system and the name of the instance, I can run this complete block by doing Control-Enter, and then a new DSS structure has been created with my new system name and new instance name. I see that it has already 9 states, 3 input variables, and 14 output variables. It is still a non-delayed system. What I would like to show is that this is the DSA structure that has been created. It has the same fields as for the RLC circuit, but in any case, what I can do is go to DSA, then the functions field, and then open. Just doing this will directly open all the files, so the data file, the variables, harmonic domain, and U of t, as well as the equations naturally. So let's quickly go over these, starting with the lists of variables. So for this single phase MMC model, I have 3 inputs. I have the alternating voltage, direct voltage, and the reference for the alternating current. I have a number of states: the alternating current, circulating current, upper arm sum capacitor voltage, lower arm sum capacitor voltage, a filtered version of the direct current, as well as 4 control variables, 2 that are related to the alternating current controller, and 2 that are related to the circulating current controller. I have defined on top of this a number of outputs. Some of these outputs are states, for instance, the alternating current, but I have also access to the upper arm current, lower arm current, the references for the circulating current, as well as differential mode and common mode voltages references. Plus, below you'll see a number of additional variables. I can mention in particular the instantaneous power, the direct current, the modulation or insertion indices for the upper arm, lower arm, and naturally all of this is for a single phase MMC. So I have not specified A, B, or C. It's just one phase. This system is still non-delayed, so I have not filled the cells related to the 2 delay variables and the delayed variables. However, we will start talking about calculation of eigenvalues, calculations of frequency responses. This is when linearization comes into play. The system that we will consider now, this single phase MMC, is nonlinear. So after linearization, we will be able to obtain a linearized state space representation. This linearized state space representation is defined from a given set of inputs to a given set of outputs. Although I have, for the large signal model, 3 inputs, I am interested in only 2 of them. And although I have many outputs for the large signal calculations, I am interested in only two outputs, the alternating current and the direct current. This means that, in particular, when I will be calculating frequency responses, these frequency responses will be established between these voltages and these currents. We will get back to that later with the example. Let's have a look at the equations that I have written for this MMC, this single-phase MMC. I have this time populated the if-run algebra statement. I have expressions for upper arm and lower arm currents. Naturally, for a single-phase MMC, the direct current is equal to the circulating current. I have an expression for the instantaneous single-phase power, expressions for the reference differential modes voltage. Those are expressions related to the circulating current control. These are the expressions of the modulation indices, at least their references. Naturally, the references are equal to their actual values because there is no control delay implemented between them. And lastly, I have expressions for the inserted upper arm and lower arm voltages, as well the differential mode and common mode voltages. All of these variables allow me to define some of the inputs, some of the outputs in which I am interested, but also I can rewrite more easily all the differential equations related to this particular system. Naturally, these equations are the ones that are displayed in this section of my PhD thesis, specifically these differential equations. So to access all of these variables, all of these parameters, I need to bring them from the parameter structure, from the input structure, and from the state structure. So here are our three inputs, our state variables, so 9 of them, and all the circuit parameters and control parameters. These are defined with their numerical values in the MMC data file. So this MMC data file is valid for multiple instances of the MMC, not only the single phase, but also the three phase. And so for these reasons, I have defined multiple base values for the voltages, currents, impedances. I have also some nominal values for the DC side, with a nominal value for the DC voltage and for the DC current. I have a number of circuit parameters. I let you have a look at the way they are defined in the appendices of my PhD thesis, but in any case, I have stored a per unit, or at least a scaled version of all of these parameters in the param structure. So I have, for instance, the equivalent arm resistance, I have the arm inductance, and so on. I also have a number of control parameters this time, because I'm not solving just one phase of the MMC, but also of its controller. And so here are some of the control parameters. There are more control parameters than necessary because other instances of the MMC rely on the same data file. However, it is not a problem. I can define many control parameters in this file and only use the ones that I need in this version of the equation file. Going a bit further, I see that I have defined quite a set of input parameters. Same thing. This single phase MMC does not require all of them, but I will be able to pick exactly those that I need. And lastly, I have even defined delay parameters, which I will cover later on. Again, this instance of the equations does not have any delays, so simply the toolbox will ignore the existence of this delay structure.